right, that should start the recording for us, and let's do an audio check. Do I hear myself? Yep, that works. Okay, I can unplug the headset. Gotta do that every time. Maybe it's a bit paranoid, but better safe than sorry. And let's check if I can actually see stuff from the document camera. Do I see my hand moving on the playback there? Yes, I do. All right, then we are good to go. Welcome back for those of you who have been waiting. And welcome if this is your first time here. So, as you saw right there on the little title card thing, today we are moving on to Unit 1, which is Motion in One Dimension. We do still have a little bit left over from last time. Last time we were digging into the math essentials, and I did post the solution videos in the description of the previous stream, so you can find that there if you're looking for solution videos for everything that actually had solution videos. But there are still problems that I didn't make videos for, and I didn't have the time to record one for the ones that were left over from last time. So that's what we're going to start with for today. And then the plan is going to be to go over, well, let me open the course plan real quick. So we're gonna then we're gonna revisit the topic of average velocity and average speed, and we're gonna specifically look at some common misconceptions about averages and address that stuff. Let me see, what else do I have listed here? We're going to look at position versus time graphs. We're going to talk about average versus instantaneous velocity. I think I did mention it a little bit 2 streams ago, but it doesn't hurt to reiterate on that, especially in the context of position versus time graphs. Then we're going to look at the concept of acceleration, which is going to take us to this moving man simulation, which is part of what I had you guys try out for homework, if you actually listened and tried it. I would hope that you did a little bit of reading ahead of time, but if you didn't, then that's okay. I'm probably going to teach this chapter as if you hadn't read anything ahead of time anyway, but I would still recommend pre-reading because it's easier to digest information when you're looking at it for the second time around. Anyway, let's go ahead and get started with where we left off last time with our math essentials. We were on section 2. I did 2 of the problems, and that was where we stopped. So let me switch back to my document camera, and let's bring out a fresh new page. Just one, didn't mean to pick up 2 there. And let's see what we have. So it says t equals 4r over s, and q equals 5s squared over r. T equals 4r over s, and q equals 5s squared over r. And then it says solve for s in terms of q and t. So s in terms of q and t. And also solve for q in terms of r and t. Q in terms of R and T. So a lot of times you'll have problems, especially on the free response, although it does show up sometimes on the multiple choice, where you'll be asked to express one quantity in terms of other quantities. In terms of, let me read it again, R and T. R and T. So yeah, this is something that you'll be expected to do in physics. They'll give you a couple of constants, and they'll ask you to express some variable quantity in terms of those constants. And you are allowed to use, numbers like 4 and 5 and other special constants that you will learn in physics, like the acceleration due to gravity, which we normally just write as a lowercase g. Those are things that you are allowed to include in your final answer to these types of problems if you get asked about them. But when they say in terms of a list of quantities other than constants, these quantities are the only thing that should be left in your final expression. So let's have a look at how we want to do this. Express S in terms of Q and T. So I see T, S, Q, and R over here are the unknown quantities, and R is going to have to be eliminated. If I want S in terms of Q and T, that means I can't have any R's left in what I have. So if you take this equation and just multiply both sides by S, if you do S times T equals 4R, and then you divide by T and you say S equals 4R over T, that's not good enough. They told you to express in terms of Q and T, not in terms of R and T. The R needs to go somehow. So this on its own is not enough. But is that actually a first step towards the actual solution? I'm not entirely sure. Well, I guess this is one possible path we could take, but I'm trying to think of like the most efficient path. If I want to get rid of R, I think the easiest way to do it would actually be to just multiply these together, because I see that one of them has R in the numerator and the other has R in the denominator. So if I do T times Q, then I get 4R over S times 5S squared over R. The R's cancel out. One of the S's goes. And I'm left with 4 times 5 is 20S. So T times Q equals 20S. Divide by 20, and TQ over 20 is equal to S. I think that would be the easiest way to go about solving this. But of course, you could have gone some other route. You could have continued from what I wrote over here, divided by 4 to get R equals ST over 4, and then plug that into here and do some simplifying. But I think this right here, recognizing that you can immediately cancel the R's by just multiplying T and Q, I think that's probably the easiest and most efficient solution path. And then express Q in terms of R and T. We want Q now in terms of R and T. Okay, well, we already have Q isolated over there, so all I really need to do is get rid of the S now. I'm not allowed to have S's. I want Q in terms of R's and T's, not S's. So actually, I probably shouldn't have crossed this out. If I do st equals 4r, and then I solve for s, I do s equals 4r over t, then I can plug this into the expression for q. I can do q equals 5 of 4r over t squared over r, which becomes, let's see, 4 squared is 16, and 5 times 16 is 80. And then r squared is r squared over t squared. And then all of that over r. And all that's going to do is just cancel 1 power of r there. Yeah, 80 r squared over t squared. It can be rewritten as 80 r squared over rt squared. If that looks foreign to you and you can't make the mental leap between here and here, basically what I did was I multiplied the top and bottom of this fraction by t squared. And then one of the r's cancels out, and you're left with 80r over t. Q equals 80r over t. Or over t squared, rather. Come to think of it, was I boxing my answers last time? Doesn't look like it. I should probably get in the habit of doing that because, yeah, you do want to make sure you clearly mark what your final answers are on your AP exam so that the graders know what to look at in the end. Especially if you write a lot of things that lead to dead ends that you give up on but leave on your paper for whatever reason. You don't want that to be taken as your final answer by mistake. So that takes care of, wait, does it? Yeah, Q in terms of R and T. So that takes care of that one. Next up is 4h minus 6k equals 5l, and 12h equals 30 plus 18k. It says solve for L, then solve for h in terms of k and L. So this one, I didn't think through it that well when writing it, because I think one of the symbols actually has a numerical value you can solve for, but 4h minus 6k equals 5l, and 12h equals 30 plus 18k. 12h equals 30 plus 18k. That's given to us, and then it says solve for L, and then solve for h in terms of k and L. So we want L, and then we want h in terms of k and L. In terms of k and L. Okay, so actually solving for L is kind of easy. All you have to do is divide the first equation by 5. It never said that we needed L in terms of anything specific. So yeah, solving for L is as simple as dividing by 5. So I get 4/5 h minus 6/5 k equals L, and you're done. Solving for h in terms of k and L. So actually, same thing with this one. So yeah, like I was saying, I didn't think through this one all that well. If you just divide by 12, you've got h in terms of just k, which is even better than h in terms of k and L. If I take the second equation and just divide by 12 everywhere, I get h equals 30/12, reducing by 6 would be 5/2, plus 18/12, reducing by 6 again, that would be 3/2. Okay, yeah, this is in terms of k and L. It's 3/2 k, some constants, and no L's. That still counts. But that's the trivial solution. What you can actually do with this is you can combine the two equations to solve for an actual value for, I think it was k, but let's have a look at it. So I can do, I see there's a 6k over here. So if I multiply this equation by 3, I can get minus 18k. And then if I put that together with the second equation, I should be able to eliminate k and get something. So we have, if I multiply this equation by 3, I would get 12h minus 18k equals 5L. And then if I write this with the 12h on the right-hand side, if I just flip the right and left, so if I do 30 plus 18k equals 12h. This should do something for us. If I add the two equations together, now I get 30 plus 12h minus 18k and plus 18k cancel out equals 5L. Whoops, did I write a k there? 12h is what I meant to write. Equals 5L plus 12h, and would you look at that, you can subtract 12h on both sides. You get 5L equals 30, and L is equal to 6. But not enough information to get a numerical value for h or k. And yeah, if you have L is equal to 6 over there, then I suppose another thing you could do is you could take this first equation to solve for h in terms of k and L, so alternate solution. You could take the first equation, 4h minus 6k equals 5L, and add 6k to both sides, you get 4h equals 5L plus 6k, so this is an alternate solution, and then divide by 4, and you get h equals 5/4 L plus 6/4 or 3/2 of k. And if you wanted to, you can plug in 6 for the value of L. If I do that, then 5 times 6 is 30, and 30/4, let's see, h equals 30/4 plus 3/2 k. Wait a minute, that's not adding up. (30/4) plus 3/2 k. Oh, I think I just discovered that this problem is even worse than before, unless I made a mistake somewhere. 30/4 reduces to 15/2. And that doesn't agree with this. H is equal to 5 halves plus 3 halves k. That would imply that 5 halves equals 30/4, which is definitely not true. Okay, I think what I really need to do is just strike this problem out from the list. I mean, I knew it was bad when I realized that you could solve for L, which was unintentional, but now I can't believe I've had this document for like 6 years now, and I'm just now noticing how badly written this problem was. I knew it was bad, but I didn't realize it was this bad. Okay, well, the important thing is just, the strategy, the steps, the thought process. Yeah, this is a poorly written problem, and I see all sorts of problems with it. I may have made some sort of mistake. I'll look over it later and see if I catch anything I did wrong along the way, but I think I've shown enough from it. As long as you got something like this for solving for h in terms of k and l, that's good enough for me. Or if you did, where was it? Or if you did this, I would accept either of those, even though they're not actually equivalent to each other, it turns out. But yeah, as long as you isolated h and you either got it in terms of L and K or in terms of just K and constants, you're good. Huh. I will definitely need to play around with this on my own later. Okay, next one is also kind of poorly written. So it says, well, we've got 4 equations, and it says solve for u, v, w, and z. And what you actually get is a set of solutions. So let me write down the equations. We've got u times v times w times z is equal to negative 480. And then we've got 2u plus v minus w is equal to negative 9. And then we've got w times v is equal to negative 40. And then we've got u plus z is equal to 8. So the one good thing about this problem is that you've got 4 variables, and for those 4 variables you have 4 equations. Unfortunately, the equations are not completely independent of each other, which is why you're not going to get a set answer for each variable's value. Each variable can actually have more than one possible value. There's multiple combinations, I think 4, if I remember correctly, of possible solutions. So let's go ahead and see how we would tackle something like this. The strategy when you're dealing with multiple variables and multiple equations is to try and pick 2 equations at a time such that you can reduce the number of total variables. Combine them together in such a way that you can reduce variables, and hopefully you can eliminate variables in such a way that what's left in the result can then be used with one of your other equations that also shares those same remaining variables. So let's just actually do some of these to illustrate my point here. I see this equation involves only u and z, so if I could use it with another equation that only involves u and z, I'd be good. And I don't have that, but I do have, if I look at this first equation, it's got u, v, w, and z. If I can just get rid of the v and w, then this will be an equation of just u and z. And I can do that because I can combine it with this third equation that involves w and v. If w times v is equal to negative 40, then I can make a substitution here. I can do, let me switch to, let's do orange. I can do u times v times w is equal to negative 40 times z is equal to negative 480. I can divide by negative 40 on both sides, and I get u times z is equal to, the negatives cancel out, 480 over 40, reduced by 10, that's 48 over 4, which is 12. So u times z is equal to 12, u plus z is equal to 8. I will write a copy of that over here. U plus z is equal to 8. And now I can either solve the top equation, the top of these two equations, for either u or z and plug it into the second, or I can solve the second equation for one of these variables and plug it into the top. I think I will go with the second because I don't want to create unnecessary fractions. So I'm going to do, let's do u equals 8 minus z. And yes, I cross my z's so that they don't get mistaken for 2's. Glad you noticed. I also cross my 7's so that I don't mistake them for greater than signs. 7 and greater than can be easily confused with each other, so I like to cross my 7's for that reason. Just stuff to know. And sometimes I will write serifs on my 1's if I want to avoid confusing them with absolute value bars, but when that risk doesn't exist, I'll just draw a straight vertical line, or at least my best attempt at one. Anyway, plug in 8 minus z for u up here, and I get 8 minus z times z equals 12. Just going off of this equation right here. 8 minus z times z equals 12. If I distribute, I get 8z minus z squared equals 12. I'm going to move everything to the right-hand side. So let me continue that over here. So I get 0 equals, let's see, add z squared. So I'm going to list that first. Subtract 8z. And then there was already a positive 12 on the right-hand side. And let's see, is this factorable? 6 and 2. Yeah, negative 6 and negative 2. Z minus 6 times z minus 2 is equal to z squared minus 8z plus 12. Negative 2 times negative 6 gives me positive 12, and negative 6z minus 2z gives me negative 8z. So we are good there. So already we're seeing two different possibilities. Either z equals 2, in which case u equals 8 minus 2. So u would be 6. Or we have z equals 6 and u equals 2. All right, let's pick one of these for now and see where that takes us, and then we will look at the other possibility later. So if I go with the first one, let's go with this for now. Let's go with z equals 2 and u equals 6. What can I do with that? Well, if I can replace the u with a 6, then I've eliminated it from the second equation in the original set. If I plug in a value for u, then it's gone, and this equation will only have v and w as unknowns. Also, this third equation only has v and w as unknowns. So this will probably be enough to help us solve for v and w. So if I go 2u, so 2 times 6 plus v minus w equals -9. That's one possibility. The other possibility is 2 times 2. I guess I'm solving both routes after all. 2 times 2 plus v minus w equals -9 is another possibility. So in this case it would be 12, which I'm going to subtract over to the right. In this case it would be 4 that I subtract over to the right. -9 minus 12 would be -21. -9 minus 4 would be -13. So I'm getting either, and I'm going to continue this on another sheet in a minute, either v minus w equals -21 or v minus w equals -13. Okay, let's continue this on a new sheet. Actually, we've got the backside of the current sheet. So I'm going to copy over w times v equals -40 and these. So w times v equals -40, and also was it v minus w or v minus w, -21 or -13. And then v minus w equals -21 or v minus w equals -13. All right, let's try the first route. So with the first route, I would get, how about we do this color? I'm going to solve for v and say v equals, add w to both sides, equals w minus 21. And then the other possibility is v equals w minus 13. If I substitute v into this equation, then I would get w times w minus 21 is equal to -40 as one possibility. And the other possibility is w times w minus 13 equals -40. And I'm pretty sure one of these is going to be an ugly mess. So we have, if I distribute the w, I get w squared minus 21w. And I'm going to go ahead and add the 40. Plus 40 equals 0. Over here I get w squared minus 13w plus 40 equals 0. One of these I believe is factorable while the other is not. I believe the bottom one, negative 5 and negative 8, would multiply to give me 40 and would add to give negative 13. And then the other one, quadratic formula. So let's actually write out quadratic formula for that top one. Oh, I need to unplug that thing. Give me a second. All right, I'm back. Where was I? Right, so I wanted to do quadratic formula on this. So we've got negative 21 plus or minus the square root of 21 squared minus 4 times 1 times 40 all over 2 times 1. That is for the value of w in the first case. In the second case, we have w minus 5 times w minus 8 is equal to 0. And I think you can guess just by looking at this that this was not one of the solutions I intended when I originally wrote this problem, but it's still worthwhile to look at the problem nonetheless, because you might get a situation where you have to use the quadratic formula. That's not unheard of in physics. We will see situations that call for this. So it's good to keep an open mind and not expect every quadratic equation you get to be a simple factorable quadratic. Anyway, with this one, our possibilities are w equals 5 and w equals 8. So w equals 5 or w equals 8. So this one gives us these possibilities, and if w is equal to 5, then that would mean, since w times v is negative 40, that would mean that v is equal to negative 8, or w equals 8, making v equal to negative 5. So that's one possibility, and then the other possibility over here is going to be one ugly mess. Let's see. So 21 plus or minus, what's 21 squared? 441, I believe. Calculator check. Yep, 441. And then minus 160. So minus 160 is 281. And is that a perfect square? I don't think it is. Yeah, it's not. Okay, so that's 21 plus or minus the square root of 281 all over 2. And whatever values of v correspond to that, I'm gonna leave that whole branch alone from this point on because it's too ugly to look at. But you could continue with it similar to what I did here. You could just set this equal to negative 40 over v and solve for v, and you would get your two different v values. But for this, our solution set would be, let's see, this came from the second branch, right? This came from when we chose, u equals 2 and z equals 6. So two of our solutions are was it u equals 6 or u equals 2? 2. So two of our possible solutions are z equals 6, u equals 2, w equals 5, and v equals -8. That's one possibility. Another possibility is z equals 6, u equals 2, w equals 5, w equals 8, and v equals -5. That's another solution. And then your other two solutions are going to be of the form z equals 2, u equals 6, w equals, I guess I'll write 21 over 2 plus root 281 over 2, and v equals whatever. You can solve for it if you really want to, is equal to -40 over this, basically. And the fourth one is z equals 2, u equals 6, w equals 21 over 2 minus the square root of 281 over 2, and v equals -40 over that mess. I'm just gonna leave it alone. So yeah, 4 different solutions. You've got a set of solutions for this one, no one single solution set. So again, not the best problem I ever wrote, but still has something valuable in it that you can learn, I think, which is why I still keep it in my Math Essentials. But I may have to strike out the one that came before it after realizing just how horrible it is. Anyway, moving on to the next one. The next one is quite the doozy. It requires a little bit of out-of-the-box thinking. Well, maybe more than a little bit. I don't know if I'm going to need that space up there, but I'll keep it. So we have, actually, I'll use it for the problem itself, so for the starting equations at least, hm squared plus gn squared. This is based off of an equation that you will see in the momentum chapter. Equals hp squared plus gq squared. Oh, great. And I need to make sure I carefully write my g's so that they don't look like q's, because they're kind of similar except for their tail ends. And then the second equation is hm plus gn, basically the same thing without the squares, equals hp plus gq. Gotta slow down when writing those so I don't screw them up. And it says solve for m minus n in terms of p and q. M minus n in terms of P and Q. Okay, in terms of P and Q means that the H's and the G's need to disappear somehow. This one can be a real head scratcher. It does require a little bit of staring at the problem and trying to see what you can do. But just starting with the recognition that you need to somehow get rid of h and g might give a little bit of inspiration. Another thing that might give some inspiration is the m minus n. Somehow there's going to be some sort of subtraction between the m's and the n's. Somehow that is a thing that is going to end up happening. Well, let's start with eliminating h and g. So to eliminate h and g, the strategy here would be, we're not going to eliminate them by direct subtraction. We're not going to eliminate them by direct subtraction. But one thing you can do with equations that your algebra class probably didn't emphasize is you can actually multiply and divide equations by each other, and that's going to be the key to solving this. So what I'm going to do is I'm going to group all the h terms on one side and all the g terms on another side and factor out the h on one side and the g on the other side. So I'm going to subtract hp squared on both sides and subtract gn squared on both sides for the top equation, and then I'm going to do similar for the bottom equation. Subtract hp to the left and subtract gn to the right. So I'm going to get hm squared minus hp squared equals, and over here I'm still going to have the gq squared minus gn squared minus gn squared. And then a similar thing with the second equation. I'm going to get hm minus hp equals gq minus gn. Now I can factor h out of the left for both of those equations and factor g out of the right for both. So that gives me h m squared minus p squared equals g q squared minus n squared, and h m minus p equals g q minus h. And I should, or wait, not h, n. Gotta be careful about that. My h's are starting to look like n's. Gotta make sure to draw the n's with shorter stems and the h's with longer stems. Okay. Now I can eliminate the h and g at the same time by simply dividing top equation by bottom or vice versa. I would recommend top over bottom, especially because I know I can get rid of the m minus p and g minus n. You might not already see it, but if you think about it, m squared minus p squared divided by m minus p, you can do something with m squared minus p squared that will help you divide by m minus p. Let's go ahead and divide these. H divided by h will just cancel out, and then I'm left with m squared minus p squared. I guess I'll write it over here. M squared minus p squared over m minus p equals, the g's get canceled out here when I divide top by bottom, and I'm left with q squared minus n squared over q minus n. And if you're looking at the numerators there, those are differences of squares. You can factor that. That is something you can factor. M squared minus p squared simply becomes m minus p times m plus p. Over m minus p equals q squared minus n squared factors in a similar manner. You get q minus n times q plus n. And the denominator is still q minus n. m minus p divided by m minus p is 1. Similar story for q minus n over q minus n. And that leaves us with m plus p equals q plus n. Now we were solving for m minus n in terms of p and q, so all I have to do now is subtract n to the left to get my m minus n and subtract p over to the right. So I'm left with m minus n equals q minus p. And there you go, it's done. This is the relationship between the initial and final velocities of two objects that collide with each other elastically, something you will learn about in the momentum and collisions unit. Basically, when two objects collide with no energy loss, assuming it's a one-dimensional collision and not a two-dimensional one with angles and stuff, assuming the only two directions are left and right. If two objects collide with each other, what this will end up telling you, as you'll see later, is that the difference in their velocities before they collided is going to be the opposite of their difference after collision. Basically, the rate at which the distance between them was closing before they collided is going to be the same rate at which the distance between them grows after their collision. And you'll see how that actually works out when we get to that chapter, but just a little bit of an appetizer for you. All right, one more, and then we can talk about motion. This one says 3 sine squared of theta plus cosine of theta is equal to -1, and it says solve for theta. I hope you remembered the trigonometry stuff that we covered towards the end of the previous stream. So we have 3 sine squared of theta plus cosine of theta equals -1, and it says find theta. Solve for the value of theta. It does have an actual numerical value that you can solve for. I'm trying to remember if I said... What did I say last time about this? I think I remember at some point I said something about how, when we were here, when we were doing sine theta over cosine theta, if you're trying to solve for a theta that's inside a bunch of trig functions, then what you want to do is try and simplify your trig functions and combine them into just one type of trig function. So get them all to be sines, or get them all to be cosines, or get them all to be tangents, if you can. That's easier said than done in a lot of cases. So that's going to be the same strategy that we use here. If you're trying to solve for a theta that's stuck inside of a trig function, you need to get all the trig functions to look the same. You need to get it all to be sines or all cosines or something like that. So if you remember from last time, or if you know it well from pre-calculus, we have the Pythagorean identity, which tells us, as I proved last time, sine squared of an angle plus cosine squared of that same angle. It doesn't work if the two angles are different, is equal to 1. Sine squared of an angle plus cosine squared of that same exact angle must be equal to 1. If I rearrange this, I can say that sine squared of an angle is equal to 1 minus cosine squared of that angle. If I go ahead and do that here, I will get 3 times 1 minus cosine squared theta plus cosine theta equals -1. And then I have, if I distribute the 3, I would have 3 minus 3 cosine squared plus cosine theta equals -1. Well, we still have a bit of a dilemma because cosine and cosine squared, there I do have an inverse cosine button, but I don't have an inverse cosine squared plus cosine or anything of that sort. So what can I do to simplify this expression even further? Well, if you stare at it long enough, you might notice something. A trig function of an unknown angle is itself an unknown. Sine of some unknown is itself an unknown. Cosine of an unknown is itself some unknown. So we can say, let's say for example I use the variable u. Let's say I say u is equal to cosine of theta. U is a variable, and cosine of theta is also a variable. I'm just relabeling, I'm just renaming so that this is easier to look at. So if I rewrite this now with cosine theta replaced by u, then what I get is 3 minus 3 cosine squared theta, that's just cosine of theta all squared, or in other words, that is u squared, plus cosine theta is just a direct substitution of u equals -1. Well, this looks like something we know how to solve. This is just a quadratic equation. So if I go ahead and continue, let me switch colors. Let's start on a new line. If I go ahead and move everything over to one side, I think I'm going to move everything to the right so that I have a positive leading coefficient, then I'm going to be left with 0 equals, I'm going to do 3u squared, and then subtract a u, and then we already had -1 on the right, and we're subtracting another 3 from it, so that's -4. Okay, and is this factorable? Let's see, 3 times -4 is -12, and the factors of -12 that add up to -1 would be -4 and 3. So -4 and +1, because 3u minus 4 and then u plus 1, like that, would equal 0. Let's see, did I do that right? -4 u, and then 1 times 3u is plus 3u, which gives us, -u. Okay, so our possibilities are u equals 4/3, or u equals -1. So our possibilities are cosine theta, right? U was just a temporary substitute for cosine theta. So either our cosine theta is equal to 4/3 or cosine theta is equal to -1. Well, it turns out that only one of these possibilities is valid. Those of you who know your pre-calculus or trigonometry should know this. Cosine theta equals 4/3 is impossible. Cosine theta equals 4/3 is impossible. If you try to do inverse cosine of 4/3 on your calculator, you will get an error. Cosine theta only falls between -1 to +1. It cannot be less than -1 and it cannot be more than +1. 4/3 is more than +1. It doesn't work. So cosine theta equals -1 is the only possibility, and that leaves us with theta equals 180 degrees. Theta equals 180 degrees, or pi if you're working in radians. And for those of you that are confused about how a 180 degree angle can have trig functions associated with it, you might have not taken pre-calculus yet or trigonometry. So what I would encourage you to do, if that's your situation, is just look up some videos introducing the unit circle definition of the trig functions. Unit circle definition of trig functions. And it will explain how angles outside of your 0 to 90 degree range can have sines or cosines associated with them. Unit circle definition of trig functions. So that's what you might want to look up if you find this theta equals 180 degrees to be troubling. We are definitely going to see angles outside of your traditional 0 to 90 degree range, and we will have to work with their sines and cosines and sometimes even tangents. So that's an idea you ought to get comfortable with now before we start seriously encountering these situations on a regular basis. But that's all I will say about it for now. Let's go ahead and move on to our next topic. So we want to now reiterate on the concepts of average velocity and average speed. We already talked about them a little bit. We went over their definitions. Average velocity, the bar above the V represents average, and sometimes people just write AVE as a subscript instead. Average velocity is equal to total displacement. I'm just going to call it delta R in this case, over change in time or total time, however you want to think about it. And average speed, which is a scalar, is equal to total distance over total time. I use the delta R here instead of a delta X or a delta Y or whatever because I don't necessarily know if the change in position is going to be in the X direction or the Y direction or at some angle between both. So in case you were thrown off by that, that's why I call it delta R in this case. I will call my displacements delta R, or sometimes I'll even call them delta S if I don't necessarily know if they're going to be completely horizontal or completely vertical displacements. Sometimes I'll just call it delta x anyway, even if it's not a horizontal motion, but usually I tend to be careful about that and use delta r in cases where I'm not sure. Anyway, how do I want to go over these concepts? Let me think for a second. So we've got average velocity versus average speed. How do I want to introduce these? How about we go over somebody moving along a number line? How about we just focus on one dimension for now? Let's say we have somebody moving along a number line. We'll say that's position 0. 1, 2, 3. They're not very evenly spaced, but let's pretend that they are. -1, 2, 3, 4, and 5. And then over in this direction, 1, 2, 3, 4, 5, and I guess I have space to go even further, 6 and 7. Okay, let's say that somebody starts over here. So start, that's probably too small to even be readable, but let's say our starting point is over here at position 0, and somebody starts walking along here. And let's say I have a stopwatch timer and I write down their location in a table at different times. So here's going to be time and here's going to be position. So I start the stopwatch at 0 seconds, and at time 0 they are at position 0. They're at the starting location. Then I look 3 seconds later and I find them, let's say, over here at position 6. And I keep the stopwatch running, so then at the, let's say, 5-second mark from the stopwatch running, I find them back at position 4. So 2 seconds after they were at position 6 is how we're interpreting this. We're looking at it as a stopwatch where when you click it, it doesn't stop. It just records, what's the word for it? Like it saves times for like separate laps, but still has like an ongoing counter. I forget what the actual word for that type of stopwatch timer is. I'll have to look it up later. But yeah, we assume when you click the stopwatch, it just saves a recording of that snapshot when you clicked it, but the timer doesn't actually stop, it just keeps going. So this is 5 seconds since the start, not 5 seconds since they were at their second position. And then let's say at time, time 9 seconds in, we find them at location -3. And then at time 12 seconds, we find them back at position 0. Let's say they move like that. Okay, we want to calculate what their average velocity and average speed are for a bunch of different positions. Well, not for a bunch of positions, that's poorly worded. Not for a bunch of different positions, for a bunch of different time intervals is what I should say. So let's ask this question first. What is average velocity for part A from t equals 0 to, let's say, t equals 5. And then part B from t equals, let's say, 5 to t equals 9. And then C from t equals 0 to t equals 9. And part D from t equals 0 to t equals 12. Let's answer each of those questions. And also, we might as well, what's the average speed in each of those cases as well? What's the average speed for each of those time intervals as well? Okay, just following the formula, we see from time 0 to time 5. So at time 0, they were at the start. At time 5, they were at position 4, so they were over here. So their total displacement is their final position 4 minus their starting position 0. So we would just have 4 minus 0 for their total displacement, divided by the total time between 0 and 5 was when the stopwatch was at 5 minus when the stopwatch was at 0. 4 minus 0 over 5 minus 0 is going to be 4/5, or if you like your decimals, we can say 0.8. And that would be, I guess I didn't specify units here, but if we said x was in meters and time was in seconds, I would call this meters per second. I'm going to go ahead and say that time is in seconds. X, we'll just call it units. I don't know what the distance unit is over here, but we'll just call it 0.8 units per second. We'll be vague about it so that you can mentally replace this with whatever you're comfortable with. Meters, inches, miles, probably not miles. That doesn't sound realistic at all. Feet, whatever the case may be. So that's your average velocity, and we also have to specify a direction, so that's going to be to the right. Velocity is a vector after all, so it has magnitude and direction. Average velocity is 0.8 units per second to the right. So is that how they actually moved? Did they just walk at a fixed rate of 0.8 units per second for 5 seconds until they landed at 4? Maybe. That's a possibility, but we know that's not true because in the first 3 seconds they went all the way over to 6 and then they came back to 4. So on their way to 6, they must have moved faster. They must have moved faster on their way from the start to 6 and then quickly got to 4 before 5 seconds were up. So we know that's not exactly how they moved, so don't be misled by the average. The average velocity does not tell you anything about what their actual velocity was as they were actually traveling. It tells you nothing about how they got there. This person could have had a whole variety of velocities, both greater than and less than 0.8, that just average out to 0.8 in the end. We'll talk a little bit more about the misleading nature of averages as we go. What about average speed? So that was average velocity. What about average speed? Average speed is total distance over total time. So the total time is still the same. 5 seconds minus 0 seconds on the stopwatch, it's still 5. But what about the total distance? Well, if they traveled, I'm assuming they traveled straight to each position they visited. So this person traveled straight to 6, then immediately turned around and went to 4. So that would mean they moved 6 steps plus 2 more steps back. They traveled a total distance of 8 units. 8 over 5. And 8 over 5 would simplify to 1.6. Yeah, 1 3/5 equals 1.6 units per second. Units per second. No direction needed for speed. Average speed is a scalar after all. So yeah, this person on average moved at a rate of 1.6 steps per second. Whether they actually did that, they moved at 1.6 per second all the way to 6 and then turned around magically, like in a split second, and continued at 1.6 units per second going back to 4. I find that hard to believe. Chances are they moved a little faster than that at some times and a little slower than that at other times. But there's your calculation for average velocity and speed there. Let's quickly run through the other ones. So we've got from 5 to 9, average velocity from 5 to 9. We have at time 5, they were at position 4. At time 9, they were at position -3. So from 4 to -3 is 7 steps to the left. So I've got final position, -3, minus initial position 4, that's -7. And then the time interval, it was from 5 to 9, so final time 9 minus initial time 5. So that's -7 over 4, which is -1.75 if you want to put it in decimals. And that's in units per second. And I guess it would be redundant to call it left here because I already have the negative sign. Yeah, I guess the negative actually takes care of direction in this case. But okay, if you drop the negative and add the word left, then you have fully described the average velocity because you've given magnitude and direction. But if the problem already tells you use positive for right and use negative for left, then just the plus or minus is sufficient. You don't need to also then write the direction in words. You can do either or, but you don't want to do both. And if I had to choose, I would always prefer to just write it in words. I prefer to just write the direction in words instead of relying on plus and minus signs, since plus and minus signs have limited utility, as I described back in the first stream. Not very useful once you go beyond one dimension, where you have a 360-degree range of possible directions and 2 signs won't cut it anymore. Anyway, average speed. I told myself I was going to run through these quickly and I'm rambling, but maybe that's what people appreciate about the way I teach. I actually slow down and explain my thought process. Anyway, average speed. So how did this person move? If they started at time 5, they were at position 4, and they moved straight to position -3. There were no stops in between, otherwise I would have written them in my table. Then the average speed is just total distance. They traveled 7 steps over total time. It's the same. 9 minus 5 equals 4 seconds. So that's just 1.75 units per second. Nothing surprising there. Now, if I had started with this, you might have developed the mistaken belief that for a given interval, the average speed is just the absolute value of the average velocity. But that's definitely not the case, because we saw in the first example, in part A, we saw the magnitude of the average speed is not directly connected to the magnitude of the average velocity. So yeah, don't make that assumption. Do not assume that average speed is simply a matter of taking the absolute value of average velocity. It does work in one circumstance and one circumstance only, and that's if the object, or in this case person, moves without ever changing direction. If a person moves without changing their direction, then yes, the speed is just the magnitude of the velocity in that case. But if the person turns around, then the magnitude of average velocity and average speed will change. They'll start to disagree with each other because average speed depends on distance, which keeps counting even if you turn around, while average velocity depends on displacement, which starts counting back down if you turn back and start retracing your steps. If I walk 6 meters to the right and then I walk 2 more meters back, and my displacement doesn't care about the 6 meters forward and the 2 back. All it cares about is that I end up 4 spaces from where I started. While distance does still count when you retrace your steps and go back. So that's where the two separate from each other. That's where the two diverge. Okay, from time 0 to time 9. Bonus question to consider, and we'll go over it in a minute, but we already did the average from 0 to 5 and the average from 5 to 9. So does the average from 0 to 9 have anything to do with that then? Can I put together the information for 0 to 5 and 5 to 9 to get the averages from 0 to 9? The answer is yes, but not in the way that you might think. Some people might think that they can just add these numbers together and divide by 2 and use that as the result. That's definitely not going to be the case. Same thing for average speed. You can't just add these numbers together and take the value in between them. It's not as simple as that, but let's just calculate it the normal way first, and then we'll see how would we go about calculating it from our answers to the previous 2 parts. So over here we're going to do from time 0 to time 9. Our displacement is final position -3, starting position 0, so -3 minus 0 for average velocity, over total time. Final time is 9 minus starting time is 0. So that's equal to, I'll just keep it as -1/3 units per second. And I guess I'll just add in parentheses, that's to the left. Yeah, I probably should use parentheses instead of commas here, since I already have positive and negative to indicate direction. Putting it in parentheses makes it a little bit less redundant looking, I guess. And then average speed is going to be total distance over total time. So total distance, they went from 0 to 6, that's 6 steps. Then from 6 to 4, that's 2 steps back, so that's 8. And then from 4 to -3, that's 7 more steps. So 8 plus 7, that's a total of 15 units that they moved, regardless of whether it was to the right or to the left. and divided by the total time is 9. And 15 over 9, I guess that simplifies to 5/3 units per second. Okay, so how do we get negative 1/3 out of the 0.8 and the negative 1.75? And similarly, how do we get 5/3 out of 1.6 and 1.75? Note that negative 1/3, or negative 0.333, is somewhere between 0.8 and negative 1.75, just not halfway in between. And similarly, 5/3, which is about 1.67, is somewhere between 1.6 and 1.75. That is important, but not all that helpful. It's just helpful in the sense that it allows you to quickly check whether your answer is actually within the appropriate range. But apart from just kind of checking solutions and making sure you didn't make any mistakes, not all that useful of an observation. I guess the other value it might have is well, I'll talk about the other value that it has once we talk a little bit more about weighted averages, which I guess we're going to start talking about right now. So the issue with adding these two numbers and simply dividing them by 2, even if the time intervals were, or rather, even if the distances were equal, the problem with adding these numbers and dividing them by 2 is that these numbers over here, the 0.8 and the 1.75 and the 1.6 and the other 1.75, the problem is that you're trying to use them to calculate a weighted average, and these two numbers for velocity contribute differently to this third number. They don't contribute equal amounts to the average, and the same thing goes for if you're calculating the average speed. They get more representation the more time that they have to actually influence the displacement or distance that this person is traveling. So let me try and illustrate this a little bit better with, let's say we had a classroom of, let's say we have a classroom of 10 people. And let's say that their scores for a test are as follows. And I'll put them in increasing order. Let's say one of them scores a 60, and one of them scores a 63, and two of them get 64s. This is probably not the most realistic grade distribution for a class of physics students. Well, then again, it might be believable. I mean, it is physics. And then you have a jump, and then you see somebody scoring 71, and another person scoring 73. We'll say that these scores are before the curve. I don't know why I chose to start as low as 60. And let's say we had, that's 1, 2, 3, 4, 5, 6. And let's say the next score is like 78. And then you have some 80s. And then a couple of people that scored 97. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. just one person scored 97. Okay, if I split this down the middle, 1, 2, 3, 4, 5, like this. If I split this down the middle, I wouldn't say that the average score of this class is 72. I wouldn't say that the average score is halfway between 71 and 31. It depends on how much each person is contributing to the average. So it's going to be somewhere between 60 and 97, that's for sure. And is it going to be closer to the 60 or closer to the 97, do you think? I would argue, just at a glance, that it's going to be closer to 60 because there's more people towards the lower end of this score distribution. There are more contributions to the lower scores than there are to the higher scores. So if I took the halfway point between 60 and 97, so 60 plus 97 divided by 2, that would be 78.5. 78.5, so over here actually. .5 is the actual average, and yet it's not half the people that scored above that score and half that scored below. That would be the median. The average, the mean, is a different thing. This is saying if everybody scored exactly 78.5, then the class average would still be the same. If they all shared their points equally, then they would end up with 78.5. But my point was, and I've kind of lost my train of thought here. Let me try and gather my thoughts for a minute. My point here is that these people don't contribute equally towards the average. These people contribute more towards raising the average on their own than any one of these people. So one person on this side, especially this 97 person, seems to be really holding up the average. This person contributes a lot more to the average than any random person below the 78.5 mark. And in fact, more than even these two other people above the 78.5 mark. I guess another way to say this is, maybe I should make up another list of numbers. Let's say, for example, that I did another 10 people, and this time instead of their scores on a test, let's say they're playing some sort of game, and we'll see how many points they score in the game. Let's say that let's say the possible scores are, I want to say 10, 20, and 30. So we get some 10s. We get a couple of 20s. One, two, three, four, five, six, 7, 8, 9. And then I guess we'll have a single 30. Okay, if I just took the highest score and the lowest score and divided them by 2, 30 plus 10 over 2, that would be 40 over 2, which is 20. Well, clearly, there aren't enough 30s contributing to the average that would raise it. There are more 10s. The 10s have, let's see, 1, 2, 3, 4, 5, 6 representatives versus only one person representing 30. So that's kind of the same as what you would have for somebody that's moving at, let's compare this to a person that's moving at 10 miles per hour for 1, 2, 3, 4, 5, 6 seconds, then at 20 miles per hour for 3 seconds, and then at 30 miles per hour for 1 second, overall, most of their distance would look more like they were driving slower than faster, because they were essentially contributing more seconds, more submissions, more scores being turned in at the lower speed than the higher one. So I would say that this lower score has a higher weight than this higher score. It's weighted 6 times harder, so I'm going to see it reflected in the average a lot more. If I add these numbers, let's see, we've got 6 times 10, so 60, plus 3 times 20. Actually, yeah, let me write out that process. So calculating the average here, I would do 6 times 10 plus 3 times 20 plus 1 times 30, all divided by the total number of contributions, the total number of scores, divided by the 10 people. So that's 60 plus another 60 plus 30 is 150 over 10, and I get, for my average, I get 15, which is not halfway between 30 and 10. That would have been 20. It's even lower than that. It's a lot closer to the 10s than it is to the 30. That's all due to the 10 being weighted more. This is not too different from what we have to do to calculate an average velocity of some big interval by combining the average velocities of 2 smaller sections of that one big interval. So the way I would do this over here is similar to what I just did here. I would take my 0.8, so if I want to calculate, let me do it down here. If I want to calculate V average from 0 to 9, V average from 0 to 9, what I actually want to do is I want to take my V average from 0 to 5, my 0.8, and I want to multiply it by the amount of time that it spends contributing to the average. Kind of the same way that I took the 10 and multiplied it by the 6 times it was added to the pool of total points. I would take the amount of time over here, the 5 seconds, I would multiply by the 5 seconds that it spent contributing. I probably should have written it as 5 times 0.8 so that it would be in line with what I wrote over here. But anyway, add to that the contribution of the second part. So I was moving at negative 1.75 for 9 minus 5, or 4 seconds for the second part. So I would do 4 times negative 1.75, since my quote-unquote score of negative 1.75 was being added to the average over the duration of 4 seconds. You could say it was contributed 4 times, once per second, and divide that by the total number of contributions, which in this case is 4 plus 5, a total of 9 seconds, and we should get, if I did this right, 0.8 times 5 plus 4 times negative 1.75. I'm getting negative 3 for the top over 9, which reduces to negative 1/3 as expected. And you can do something similar with average speed. You would take your 1.6 times 5 seconds and 1.75 times 4 seconds, and then divide that by 9, and that should give you 5/3. I'll leave that for you guys to do on your own. one more, and I think this will probably be the most intuitive example of weighted averages, is grades. If you look at your grade book in school, usually your teacher will have it broken down in a fashion similar to this. You might have, for example, let's say 10% of your score is attendance. And 20% of your score is like some sort of project unit. And maybe, let's see, 10 and 20, that's 30, so that leaves us with 70. We'll say 40% of your score is homework. And the remaining 30% is tests and quizzes. So if I scored let's say I had perfect attendance and I got 100% on my attendance, and I did okay on my project and I got 90%, but then I didn't do so well with the homework and I got 70%, and I got, maybe after cramming, I got 75% on tests and quizzes, I wouldn't just go 100 plus 90 plus 70 plus 75 and divide that by 4. I wouldn't do that, because this 100% might not be worth as much as, say, this 70%. In fact, I'm pretty sure we can prove that it's that the 70% is worth more points. The homework points are 40% of the grade, so they have 4 times as much weight as attendance. So yeah, 70 times 4 is a lot more than, or I should probably say 70 times 40 is worth a lot more than 100 times 10. 100 times 10 is just 1,000. 70 times 40 would be 2,800. So what you would actually do is you would calculate your score, you would calculate your grade by multiplying each of these by their weight. So you do 100 times 10%, or 10 over 100, and then 90 times 20 over 100, and then 70 times 40 over 100, and 75 times 30 over 100 to get your final grade, which I guess I'll go ahead and calculate. 100 times, I guess that would be 0.10, plus 90 times 0.20, plus 70 times 0.40, plus 75 times 0.30, and I'm getting, well, would you look at that, 78.5%. That's 78.5%. That's a B minus, right? Maybe it'll get curved, I don't know. But yeah, bottom line is the average velocity is not the average of the velocities. It's a weighted average, and it's weighted by time. And the same thing goes for speed. Average speed is also weighted by time. The more time you spend traveling at a certain velocity or speed, the more that velocity or speed will be reflected in the overall average. If I travel this, a really, really simple example that's super intuitive without doing any math. If I travel 60 miles an hour for 59 minutes, and then I travel at 1 mile per hour for 1 minute, then my average for that full hour is probably going to be a lot closer to 60 miles per hour than it is to 1. It's probably going to be something like 59.99 miles per hour if I actually did the math and calculated it. We'll see more examples of this as we go. Anyway, let's finish up the problem that I started us off with so that we can actually get a move on with this and get to the topic of acceleration. I definitely want to at least introduce acceleration before I wrap up today's stream. So from time 0 to time 12, what is the average velocity? Well, this one should be pretty easy if you just take a quick look at the change in position. From time 0 to time 12, starting position is 0, final position is 0, total change in position is 0 minus 0 is 0. It doesn't even matter how much time passed. So I guess 0 minus 0 over 12 minus 0 equals 0. If you move around and go back and forth and eventually you land at the same spot that you started, then on average you didn't move at all. This is just another example that illustrates how misleading averages are. On average, you didn't move, but we know this person actually moved around. So, yeah, be very, very careful with averages. I know a lot of people like to talk about the average person, this and that, for whatever it is they happen to be talking about in day-to-day life. But what they should probably be saying isn't the average person, but the typical person. That's just a little nitpick of mine. Anyway, a velocity of 0 doesn't really have a direction to it, so no direction needs to be specified for a vector whose value is 0. Average speed, on the other hand, is still a meaningful concept here. So we took 15 steps in the first 9 seconds. I remember that from part C. And then from there, which had us at -3, we go back to 0. So we go 3 more steps on top of the 15 steps that led us to -3. So that's a total of 18. So average speed, total distance traveled would be 18 over total time is 12 seconds equals 3/2 or 1.5 units per second. All right, there's a simple, well, maybe not so simple. I kind of complicated it a little bit with my discussion of averages, but an otherwise simple example of working with average velocities and average speeds. Okay, where did I put my books? Oh, there they are. So now I want to dig a little further into this idea of weighted averages. Let's go ahead and look at a problem from one of my books. It says, 2 boats start together and race across a 60-kilometer wide lake. So we have a lake that is 60 kilometers wide. And we have 2 boats We've got boat A and boat B. They start together and boat A goes across at 60 kilometers per hour. So boat A goes across at a constant 60 kilometers per hour. So that's forward. And it comes back at 60 kilometers per hour. And then 60 kilometers per hour on its way back. Boat B, on the other hand, goes across at 30 kilometers per hour. So boat B goes at 30 kilometers per hour on its way forward. It says its crew, realizing how far behind it is getting, returns at 90 kilometers per hour. So 90 kilometers per hour on the way back. And it says turnaround times are negligible, so don't worry about the time it takes for the boats to turn around and go before they go back. We'll leave that out of the problem just to simplify things for ourselves. And it says the boat that completes the round trip first wins. That's how races work. Part A, which boat wins and by how much? Or is it a tie? And then part B, what is the average velocity of the winning boat? Part B, if you're paying close attention, you should be able to answer immediately. Part B, you should be able to answer right away. What is the average velocity of the winning boat? They start here, they go here, and then they come back here. Regardless of which one wins, their ending point is the same as their starting point. They start here and they end here, which means their displacement is 0, which means their average velocity is 0. So part B, instantly done if you recognize that simple fact. Their average velocity is 0. Average velocity for anybody that takes a round trip, anybody that meanders and eventually comes back to where they started. Their average velocity for the whole entire time they were in motion would be 0. Average speed, on the other hand, is a separate question, but they did not ask us about average speed here, so we're good. Although I might ask that as a bonus question in a minute here. So they said boat A goes across at 60 kilometers per hour and returns at 60, and boat B goes across at 30 and comes back at 90. Which one wins, or is it a tie? If you said it's a tie, you didn't pay attention to my spiel a few minutes ago about weighted averages. Going at 30 kilometers per hour and then at 90 kilometers per hour would lead to an average speed of 60 kilometers per hour if you traveled at each of these speeds for the same amount of time. But I know for a fact that these two speeds were not used for equal amounts of time because they were used for equal distances instead. And when you cross the same distance at two different speeds, you're going to get two different times. Traveling 60 kilometers at 30 kilometers per hour would take 2 hours, while traveling that same 60 kilometers back at 90 kilometers per hour would take, a little less than an hour, 2/3 of an hour, 40 minutes. We can do the math in case you couldn't keep up with what I did in my head just now. So what I want to do is say, total distance is 120 kilometers. I'm just going to use speed here. So total distance is 120 kilometers, and boat A takes, so I'm going to do speed equals distance over time. I'm going to say speed of the boat on the way forward for boat A, S-A forward, equals 60 kilometers forward over, I guess I'll call it time A forward. By the way, this is good practice. I should probably talk about this. Practice naming your variables well. If you name your variables carefully, then it makes it easier for people grading your work to see what you're trying to do. And it also makes it easier for you to see what you did, because when you look back at your old papers and you look at your old work, if you can't follow what you did, then that's not good. So definitely come up with some system. It doesn't have to be my way of doing it or your teacher's way of doing it. Come up with something that makes sense to you as a sort of system for how you name your variables. Just wanted to make that side comment. So I already know the speed forward is 60, so I can go ahead and substitute this. I can go ahead and substitute this with 60. And if I do that, then multiply the time over to the left and divide this speed over to the right. So time is going to be 60 over 60. So T-A forward is going to equal 60 kilometers over speed A forward is 60 kilometers per hour. $60 over 60 is 1, kilometers over kilometers cancel out, and 1 over hour is just an hour. So that leaves us with T equals 1 hour forward. 1 hour forward. Going back, it's pretty much going to be the same thing, so I'll just skip to the rearranged formula. TA back is going to be, well, it's 60 kilometers going back, and they go back at 60 kilometers per hour, so that's 1 more hour. I'm not always going to write the units in my equations as I solve them, by the way. I'm just doing that for now. But I usually tend to skip on that unless I want to really be careful and make sure my units come out right. I'll probably do that in problems where I'm not sure what units to expect. But a lot of the time I'm going to be using standard units, and I will know for sure what units will come out of my calculations. So in those cases, I don't bother writing the units in my in-between steps. Anyway, total time for the whole round trip, TA total, 2 hours. Okay, do a similar calculation for B. So speed of B, whether it's forward or backwards, is equal to the distance, which is going to be 60 kilometers, divided by the time. So we can do TB forward. If I rearrange this equation, multiply the T over to the left, divide the S over to the right, same as we did before. TB forward is equal to 60 kilometers over 30 kilometers per hour. 60 over 30 is 2 hours. So they've already lost by the time they cross over. Boat B has already lost because it has already taken the same amount of time to travel 60 kilometers that boat A took to travel both the 60 kilometers forward and back. So already boat B has lost, In terms of distance, it lost by 60 kilometers. In terms of time, it lost by, well, I guess we're about to find out. How much longer after the 2-hour mark does it take for boat B to come back? TB back equals the distance back is 60 over the speed back is 90 kilometers per hour. 60 over 90 equals 2/3 of an hour, or 40 minutes. So yeah, boat B is late by 40 minutes. It takes 2 hours and 40 minutes to travel the same path that boat A traveled in just 2 hours. And there you go. What are the average speeds of the two boats? That's a bonus question from me. What are the average speeds of the two boats? Assuming that their speeds were constant on the way forward and then constant on the way back. Total distance over total time is the formula. So speed of boat A, average speed for the full trip, is total distance 120 kilometers forward and back divided by total time, 2 hours, equals 60 kilometers per hour. That's not a surprise. If you only travel at one speed the whole entire time, then that is your average. If I had a classroom that was very well coordinated and every single person in that room took the same test and they all scored 90, exactly 90, every single one, then the class average is 90, but it's also suspicious. Okay, what about average speed of boat B? So for this one, same total distance, 120, but the total time is 2 2/3. Or, let's see, 2 2/3, if I convert that to an improper fraction, that's 6/3 and 2/3, so 8/3. Which is the same as 120 times 3/8. 120 over 8 is 15, and 15 times 3 is 45. 45 kilometers per hour. Does 45 make sense? It is between 30 and 90. So it does fit. It is between the highest and the lowest speeds. And it's closer to 30 than it is to 90. Halfway between 30 and 90 would have been 60. Less than 60 is closer to 30, and that's what I would expect because you spend more time at 30 kilometers per hour than you do at 90. So yeah, that does make sense, intuitively at least. That gives me some reassurance that my math was right, but you can never be too sure, so always make a habit of double checking and triple checking your answers whenever you do these sorts of problems. Okay, now let's look at graphs. Now let's look at a problem involving graphs. What is that on my table? Oh, I think it was a bug. Hold on. I need to go wash my hands of it. So tiny, I almost mistook it for a speck of dust. I don't even know what that thing was. Anyway, graph problems, position versus time graphs, and what we can glean from them. I guess I want to start on a new page for this, yeah. Okay, position versus time graphs. So I'm just going to copy one from my book over here. So we have a graph that counts up to, it looks like 10. So we've got 2, 4, 6, 8, 10. And that's position in meters. So this is describing something that moves horizontally. And then for the horizontal axis, we've got time in seconds. Okay, so we're talking about somebody like this person over here, except instead of writing their data on a table like I did over here, this time we're actually going to draw their data on a graph. So let me mark some key points and see what I can do with this problem. I want to keep the orange for a second, and I want to do 1, 2, 3, 4, 5, 6. Definitely not to scale, but should be a good enough sketch. And then, yeah, we don't need to go past that, but I'll just, for the sake of OCD, I guess, I'll write out the 10 over there. And I should actually put down the -2, -4, and -6 on this side. -2, -4, and -6. Okay, now let's draw the graph. So we have a sharp point at 2, 10, and at 4, 5, so between 6 and 4, so something like that. And then 5, 5. And then it goes all the way down to -5, -7, -5, I should say. 7, -5, so -5 over there, and 7, something like this. And then it just goes to 0 at 8. It goes to position 0 at 8. Let me grab my ruler for this. I should probably just make a habit of bringing my ruler to the table up front from now on. Watch me forget to do that. It's not like it takes that long for me to get up and pick it up off of the table. But anyway, starting from 0, 0. We have that, then goes down that way. I don't even think I need the ruler for this, but there we go. I think I drew that a little off because it's supposed to cross through the axis at 6 exactly. And then yeah, something like that. And then it stops here. I accidentally drew a little bit more over there. Let me scribble it out. Yeah, the graph just ends over there. Okay, so let's interpret. What are we even looking at? So this is somebody who was moving horizontally. I guess it might help to draw a number line to accompany this. So let's see, they go from -5 to 10. -5, 4, 3, 2, 1, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So at time 0, they start here. They start at position 0. It looks like they move to position 10 at first. They move straight to position 10. Then they go from position 10 straight to position 5. Then it looks like they stay at 5 for 1 second. And then from there, they stay for 1 second. I'll just write a squiggle. And then, after staying for a second, they decide to continue moving back until they hit -5. So then they move to -5 like that, and then they instantly turn around and go back from -5 to position 0. And this is where they stop. That's basically what they did. And we can see on the horizontal axis how much time it took them to make each of these moves. Now, the fact that these are straight lines tells us something really important. It tells us that each of these moves that the person made were made at a constant velocity. They did not slow down, they did not speed up whenever they were taking one of these, I guess, 1, 2, 3, 4 steps. I guess 5 steps if you count the part where he stuck around for a second. Each of those steps occurred at a constant velocity, which is not entirely realistic because you can't just instantly change your velocity like that. You have to, you can't just go from 0 to 5 meters per second, for example, without, at least for a split second, passing through all the other speeds between those numbers first. But anyway, for the sake of a simple problem, we will assume that they have some sort of instant velocity change power. So, yeah. The question is asking us to find the average velocity in the time intervals from 0 to 2 seconds, 0 to 4, 2 to 4, 4 to 7, and 0 to 8. I don't know if I'm going to do all of those, but we'll pick a few and do them. The important thing for reading off of a velocity versus time graph, especially if it's got nice lines like this and it's not all curved, is just recognize that slope gives you your exact rate of change. If you have a straight line between 2 points on a position versus time graph, then that represents a constant velocity or speed. And you can just calculate it from the slope. And we will see that when we actually look at part A. So it says, what's the average velocity from 0 to 2 seconds? Okay, change in position. So position final minus position initial. Position final was 10 minus position initial is 0 over change in time. Time final was 2 seconds and time initial was 0 seconds. 2 minus 0. Well, what is that? That's basically delta y over delta x, except this is x and this is t, so I guess it's delta x over delta t here. It's the formula for slope. It's the formula for the slope of a line. Specifically, it's the slope of this line. So 10 minus 0 over 2, which is 5. And we know the units are meters per second because the numerator is in meters and the denominator is in seconds. And that's going to be in the positive direction, or I guess we'll say forward. Actually, no, I don't need to say that here. I'll do what I did before. I'll just put it in parentheses. The fact that it's positive alone tells us everything we need to know, because this is a one-dimensional motion where moving to the left is reflected with a negative. Anyway, next it's asking us, what is the average velocity from 0 to 4? What is the average velocity from 0 to 4? Okay, so at 4 seconds, they are over here at the 5 meter mark, minus initially at time 0, they were at position 0. Over total time is going to be 4 minus 0 equals positive 1.25 meters per second. In other words, still in the forward direction. Okay, well, where's the slope in this? Well, if this person had traveled directly from position 0 to position 5, then the graph would have looked like this. So 1.25 meters per second is the slope of this dotted line. If they had traveled directly from 0 to 5 over the course of 4 seconds, the slope of that dotted line would have been the average velocity. As we can see, the fact that the graph does not look like this line is just further confirmation of what I've been repeating like a broken record all day today. The average velocity does not necessarily have to be the velocity at which the person traveled. In fact, there is no point on this graph where the slope is equal to this slope. At no point at all in this graph does that ever occur. We've got this slope, we've got this negative slope, we've got a 0, we've got this negative slope, and we've got that positive slope, which I think might actually be the same as this one, if I'm not mistaken. They look parallel to me, but I could be wrong. If they're not exactly the same, they're pretty close for this first line and this last upward line. But anyway, let me see, are there any other parts of this that are interesting? 2 to 4 seconds, no, we don't need it. 4 to 7 seconds, from 4 to 7. That one might be interesting, from 4 to 7 seconds. Well, it's headed downward, so I expect it to be a negative slope. So yeah, let's calculate it. V average from 4 to 7 seconds is going to be position at 7 seconds is -5 minus position at 4 seconds is 5 over time at 7 seconds is 7 minus time at 4 seconds is 4. So that's -10 over 3, -10 thirds meters per second, or if you prefer, -3.333. The negative indicating that it's backward motion. But yeah, so as long as you're good at interpreting graphs in general, this shouldn't give you too much trouble. Slope on a position versus time graph, when you can actually calculate it, gives you the velocity for any point along that line. So at every moment over here, what did we calculate it as? 5 meters per second. So at every moment until this person reaches their first turning point, at every single one of those points, the person is actually traveling at 5 meters per second. As long as the slant of the line isn't changing, their velocity isn't changing. So you can actually calculate their instantaneous velocity at each of these different moments at any point between time 0 and time 2. Their instantaneous velocity is 5 meters per second. Now, at 2 seconds, you can't really get their instantaneous velocity, because are they moving at 5 meters per second, or are they moving at the negative velocity after turning down? In reality, this peak would actually smooth out like this over the course of a split second. They would be at 5 meters per second, 5, 5, and then over here they slow down to 4, 3, 2, 0 once they reach this peak, and then they start turning back and growing into the negative velocity. That's what would happen in real life, but on this graph, when you see sharp turns like that, you can't calculate the slope of a sharp turn. So yeah, you can't say anything about how fast they're moving at the exact moment of t equals 2 seconds. But everywhere between 0 and 2, it's just the slope of that line. Anything else I wanted to say about graphs? Well, I might as well draw another graph and talk about instantaneous velocity. So if you've got straight lines on your graph like this, then the instantaneous velocity, as long as you're not at some sort of sharp turning point like here, or here, or here, or here, or here, as long as you're somewhere between those turning points, you can just use the slope of whatever line you happen to be on. But what if you're not on a line? What if you're on a curve? What if your position versus time graph looks like this? Well, then you can still calculate the instantaneous velocity if you are very precise with your measuring equipment, if you're very precise with your ruler, and you just pick your points carefully and really zoom in on them and draw the slope of the tangent line to that point. So if I was super precise with this, which is nearly impossible because I'm only human, then I could draw a line that just barely grazes the curve at this point, and whatever the slope of this line is, that would be the instantaneous velocity at that moment. And then for the next moment after that, you would have to, draw another line with another slope. Let me use a different color for it. You'd have to draw another line with a different slope and calculate that new slope. And they might ask you to do this on the AP exam. They might ask you to use the slope of a tangent line to a curve to approximate something. And if they do ask you to do that, they're not going to nitpick too heavily on the exact number you get. Like, some students will draw their line like this. Others might draw it slightly off like that. Some students might get it a little lower like this. But as long as you're somewhere within this range, like they have some sort of reasonable range where as long as you're actually trying to get it somewhat precise, your answer will count. So you don't have to worry too much about the exact numbers you're getting. But yes, they will sometimes ask you to calculate some sort of instantaneous rate of change by taking the slope of a tangent line to a curve. So that is something to keep in mind. Instantaneous velocity at a given moment is the slope of the graph at that moment. And if it's not a straight line graph, you just draw a straight line that grazes the graph at that point and calculate the slope of that. Okay, I think I need to flip my lights on. Actually, no, it looks just fine on my screen. I don't think I need to adjust the lighting here. I think we're good, but I might want to flip the lights on in like half an hour or so because it is starting to get a little bit dark for me. What did I want to do next? I'm looking through these problems and I don't see any that I want to do immediately. Yeah, I think it's finally time to talk about acceleration. It's time to talk about how velocity changes. So let me open up the homework assignment here, and let me actually switch screens, and let's have a look. So you can ignore the part about the group exercise thing. You can do this just fine on your own. If you open the link to the PhET simulation, you should get this page, the moving man simulation, and you can either download it to your computer or you can just run the browser compatible version. I'm going to run the browser version. Okay, and let's see. So there's the introduction mode that you can play around with just to get a feel for how it works. You can drag the man left and right and make them move around, and the position, velocity, and acceleration sliders will reflect whatever you're doing with him. You can have him crash into these walls, which will stop him, or you can get rid of the walls and just make him even run off the side of the screen. In many cases, never to return. You can switch on the velocity and acceleration vectors so that you can actually see the vectors drawn on him as he goes. It's kind of chaotic if you just drag him around with the mouse, so I'm going to go into the charts mode. Yeah, click on the charts tab, click on the man and drag him to the left until he crashes into the wall. Clear the charts, pause the recording. And what were the numbers I wanted to start off with? I think now we can get rid of the wall. You can click the plus to put the walls back on if you mess something up. Okay, velocity of 1, acceleration of 2, and check the show vector boxes. So velocity of 1, and show vector, and acceleration of 2, and show vector. Okay, so we've got the red vector is a little bit harder to see under the green one, but what you will see if I run this is that the size of the green vector stays the same while the red one, as you saw, was growing. And if you look at these charts, then you see three different types of graphs. You see the velocity graph is a straight line that just goes up. The velocity value also has changed from what I put in the beginning. I started with 1 and, well, look at it now. It's at 16.583. If I zoom in on the acceleration graph, okay, that's as far as I can zoom in. Well, what you should be able to see here is that the acceleration graph is just a horizontal line. It doesn't go up or down, which makes sense. The acceleration stayed at 2 the whole entire time. So the acceleration graph is just a straight horizontal line. Velocity is a straight slanted line, and then the position graph looks like some sort of quadratic function. It looks like the right half of some sort of parabola, which is not a coincidence. But yeah, if you played around with this, I'm assuming you did, then you should have been able to get the answers that I'm going to go over right now. What happened to the acceleration vector? Stayed the same. Red vector got bigger. Yeah, I don't think you need me to go over the answers for this. How did velocity change in those first 2 seconds? It would have gone from 1 meter per second to 5 meters per second, so it increased by 4 meters per second. Yeah, I don't think I need to go over all of this stuff for you guys. I mean, if you want to ask questions in the comments or anything like that, you can. But I'm pretty sure most of this is self-explanatory and easy to do. Instead, I want to pay attention to these check your understanding questions. For each set of statements below, determine which one in each set is not true. If an object starts with a negative velocity and is moving with a constant positive acceleration, it will eventually stop and turn around, its speed will always increase, or its velocity will always increase. If it starts with negative velocity, that is, it started moving to the left, then a positive acceleration will first decrease its leftward motion and then start increasing its rightward motion. And between that leftward and rightward motion, there's a pause, there's a moment for a split second where they're not moving at all. So it will eventually stop and turn around. Speed will not always increase. Velocity will always increase. It will start off as negative and become less negative. That's an increase. If it goes from -5 to -3, that's an increase. So yeah, velocity is always increasing. If it starts off negative, it becomes less negative, and if it starts off positive, it just becomes more positive. So velocity is always increasing when acceleration is positive. I probably should have gone over at least the definition of acceleration before discussing these questions. Yeah, let me do that. We'll come back to this. Let me go over the definition of acceleration. And yeah, I think I want to flip the lights on. Let's define acceleration. So acceleration is oh goodness, I might be coming down with something. Man, it just hit me out of nowhere. Must be the changing temperature. Anyway, acceleration. not like textbook definition, but basically it's a change in velocity, occurring over some amount of time, You need time for things to accelerate. Things can't just change their velocity instantly. Like, again, these sharp turns that I was talking about, not realistic. Over some amount of time. Okay, so what is that? That is the weirdest looking M I've ever written. A change in velocity occurring over some amount of time. So, change in velocity. Now, we have to remember that velocity is a vector, which means there are 3 different situations where we can claim an object is accelerating. Because to get a change in velocity, all you need is a change in magnitude, or just a change in direction, or you can have a change in both. So a change in magnitude, that's the easiest one to understand. If you step on the gas pedal of a car, you change the magnitude of your velocity. Assuming you're just moving straight, you're not changing direction, you just step on the gas pedal, then all you're doing is, I guess in the case of a car, increasing the magnitude of the velocity. And if you step on the brakes, that's also a type of acceleration. Sometimes we call it deceleration, but you can also think of it as negative acceleration. In physics, deceleration is just a specific case of acceleration. So that's a change in magnitude only. You can have an acceleration where only the direction changes. The example of that would be what I did in the first stream. I believe I asked the trick question of a car driving around a roundabout, and we said that it can't drive around there at a constant velocity, it can drive around there at a constant speed. It can drive around at a constant speed. So the magnitude stays the same, but the direction of the car is always changing. That means that this car, even though it's not speeding up or slowing down, this car is accelerating. By the physics definition of acceleration, there is a change happening in its velocity. If not in its magnitude, then in its direction. So objects moving around in a circle, even if they're not speeding up or slowing down, are accelerating. That would be a change exclusively in direction, and much sooner than this scenario, we'll have a chapter dedicated to circular motion, but much sooner than this, we are going to encounter projectile motion, things fired or thrown at an angle, or launched out of a cannon, or whatever. Will travel in the air, and as they go up, eventually they reach some highest point where they're at their slowest, and then they come back down and start speeding up again. So they get launched at some sort of high speed, they slow down, they slow down, they slow down. They're also turning and changing direction as they go. At the top, they're just moving straight horizontally for a split second before they tilt back downward. So here you're having a change in both magnitude and direction. And I guess I'm not doing a good job illustrating the change in magnitude. I should have adjusted the sizes of the arrows to reflect that. My bad. Should have drawn the lower arrows bigger and the higher arrows smaller. But you can fix that on your drawing if you drew along with me in pencil, at least. If you did it in pen, then just like me, you don't really have the luxury of erasing your work. So maybe just draw it again on a separate sheet, or just write a note on top of it that the lengths of the vectors are not reflective of their magnitudes in this drawing. Anyway, that's the simple definition of acceleration. If while time passes, the velocity of something changes, whether it's in magnitude, direction, or both, the object is said to be accelerating. And there is a concept called average acceleration, which you can probably guess is going to be defined similarly to average velocity. Except this time, it's velocity's turn to be in the numerator. It's going to be the change in velocity over the change in time. Change in velocity over change in time. If the velocity starts as, say, 1 meter per second and it increases to 6 meters per second, that's a change of plus 5. 6 minus 1, positive 5. And if that happened over 2 seconds, that's a higher acceleration than if the same thing happened over 10 seconds. If you think about car commercials, a lot of car commercials will brag about how their cars go from 0 to 60 in 4 seconds or something like that. What is that? That's an acceleration. That's the average acceleration. It's 0 miles per hour to 60 miles per hour in 4 seconds. So that would be 60 minus 0 divided by 4 is 15 miles per hour per second, which is kind of a weird unit for acceleration, but those are the units. Units of velocity, which are themselves units of distance or displacement over time again. So typically, the unit we use for acceleration, the unit we use is meters per second squared. That's meters per second equals meters per second over seconds. If you multiply the top and bottom by 1 over s over 1 over s, then yeah, you get meters per second squared. That's how the units work out. But of course, you can sometimes see stranger units like miles per hour per second. So sometimes the time units of the velocity don't necessarily agree with the second time unit in the denominator of acceleration. So that's something to watch out for. It's not a common occurrence, but I have run into the occasional book problem that will do this to you, so just something to keep in mind so that it doesn't catch you off guard if you ever see it. Okay, now that we have defined average acceleration, constant acceleration is basically what we just saw in the simulation earlier, which we will probably look at again in a minute. It's when the acceleration is a fixed amount per second, and you can very easily predict by how much will your velocity increase or decrease with every second. That's the beauty of constant acceleration. It's really simple in terms of math. The downside is that without calculus, that's the farthest you can go. You can only do as much as algebra will allow you, and if you want to do more with the concept of acceleration, if you want to deal with variable acceleration, then you're going to have to learn some calculus, or at least get comfortable with having nothing more than an approximation, kind of like what we did over here with slopes. We can use slope on a velocity versus time graph to get instantaneous acceleration. We might look at that later today if I don't postpone that until next time. So let's have a look now at these questions again. So I'll go over number 1 again. It says, if an object starts with a negative velocity and is moving with a constant positive acceleration. So say the velocity starts off as something like -5. Let me actually switch to the simulation and do that. So I'm going to do clear, reset. Yeah, let me just reset everything. Move this person over here. Stop the recording. Actually, no. I want to put this person over here. Yeah, let's put them over there. Pause, clear, and let's give them some sort of negative velocity, like negative, let's say -6, for example. And I'll show the vector for that, and I'll give them a positive acceleration of, let's say, 1.5. And I want to show the vector for that. And let's see what happens. I'm going to remove the walls. And yeah, let's just play it out and watch what happens. So you see the red vector is shrinking, shrinking, disappears for a second, and then starts growing, growing, growing in the opposite direction, while the green vector remains the same. And again, if you look at the graphs, we're getting some sort of parabola for position versus time, a straight line for velocity versus time that's just going up at a steady rate, and you've got your acceleration is just a straight horizontal line, which is more clearly seen if you zoom this graph in a bit. So, if an object starts with a negative velocity or leftward velocity and is moving with a constant positive rightward acceleration, it's true that it will eventually stop and turn around, and it's true that its velocity will always increase. We saw that red graph. It's always going up. It starts negative and becomes less negative, it crosses 0, and it just keeps going up from there. So those two are true. The middle statement is false. Its speed will not always increase. Speed is the magnitude of the instantaneous velocity. It's not the magnitude of the average velocity. We went over that earlier today. Don't just take the magnitude of average velocity to be your average speed, but the magnitude of your instantaneous velocity, that is your speed. And that magnitude does not always increase. It starts off by decreasing. There's a difference between having a negative acceleration and slowing down in physics. In physics, there's a distinction between those. Negative acceleration just means acceleration in the negative direction. Whether that's a good thing or a bad thing is, I guess, up to the details of the problem. It says nothing about speeding up and slowing down. Speeding up and slowing down are about magnitude. Positive and negative acceleration are not entirely about magnitude. So keep that in mind. Those terms mean different things. The magnitude of the velocity does start off decreasing. If I were to play back, the magnitude of the velocity does decrease at first, then it starts increasing. When the magnitude is decreasing, we call that slowing down, and when it's increasing, we call it speeding up, which is not the same as accelerating and decelerating necessarily. Although the term decelerating is kind of a loaded term and is kind of vague, and you'll get the hang of it. You'll start to understand which definition of deceleration is meant, whether it's the slowing down definition or the negative acceleration definition. As you start seeing more and more problems, you'll start to be able to kind of mind read what the intentions of the authors of the book problem were thinking when they wrote the problem. I don't really like that sort of vagueness that the term has, but it's not the end of the world. You can learn your way around it. Anyway, number 2, if an object has constant acceleration, that acceleration can cause the object's speed to change, cause the object's direction to change, or cause the object to move with a constant velocity. Which of those 3 is false? If you did it at home and you guessed the third one, then you are right. The third one is not true. Remember, determine which one in each set of statements is not true. 2 true statements, 1 false. The acceleration can cause a change in the object's speed. Doesn't have to, it just can. Be careful with the wording. And it can cause the object's direction to change. It could cause a change in one and not in the other. But the point is, an acceleration can cause either of those first 2 things, but there is no way that an object can have a constant acceleration and have the object move with a constant velocity. That doesn't work by definition. A constant velocity means constant magnitude and constant direction, moving with the same speed in a straight line. The only way an object can move like that is if it has no acceleration at all. Which I guess 0 acceleration is technically a constant acceleration, but a constant value of 0 isn't really something significant enough that you would use it as your first guess as to what someone means when they say constant acceleration. You would naturally assume they mean a constant non-zero acceleration, and a lot of times book problems will emphasize and explicitly write it's non-zero, but even if they don't, you should probably assume that it's non-zero. Okay, number 3, if an object has no acceleration, then it can't move at all, it can't speed up or slow down, it can't turn around. 2 of those are true, 1 of them is false. Which one is false? A lot of people would assume that an object with no acceleration can't move at all, but that's not true. An object with no acceleration can't move if it's already not moving. But if it is already moving, then no acceleration actually keeps it moving. Keeps it moving and in a straight line, too. Acceleration is not about motion, it's about change in motion. If something's already moving, then the absence of acceleration just means it's going to keep moving. So number 1 is the false one, but what about the other 2? Can't speed up or slow down? Yeah, if you don't have acceleration, the magnitude of your instantaneous velocity cannot change. And can't turn around, that makes sense. With no acceleration, you can't change your direction. A change in direction, by definition, must be a change in velocity, which by definition must be a change in acceleration. Unless it magically happens in 0 time, but that's not realistic. Okay, and number 4, in order for a moving object to turn around, it needs to reach a velocity of 0 first, it needs to have an acceleration in the same direction as its starting velocity, it needs to travel some distance in its starting direction first. Well, let's go back to the simulation and see. So I'm going to play back, rewind, and we already have this scenario. We had a person already moving to the left, and they do turn around, but first they traveled a little bit to the left, then they had to slow down. They had a momentary pause. They have a very, very split-second stop in their motion before they turn around. there is a point, you can even see it on the graph, where their velocity does hit 0. There is a specific moment in time where they're not moving, but just for a moment. So, needs to reach a velocity of 0 first? That is true. You cannot turn around without hitting 0 first. Acceleration is a continuous process. You can't move between a negative velocity and a positive velocity without hitting 0 somewhere along the way. You have to touch all the possible values between whatever starting and ending velocity you have. If an object starts at a certain velocity and changes its velocity to something else, then it has to, for at least some moment in time, be traveling at all of the real number values in between that starting and ending velocity. For those of you taking calculus, that's basically the intermediate value theorem. And for those of you not taking calculus, don't worry about it. Just trust your intuition. You can't continuously go between two values without visiting all the values in between them first. On this graph, you can't draw a graph between, say, this point and this point without lifting the pen that doesn't visit all of the different possible values in between those 2 points along the way. And maybe even if it's some sort of weird roller coaster shaped curve, roller coaster track shaped curve, it might even go outside of that range, but at the very least you can guarantee that every number between those 2 points is going to be visited at least once. Okay, so needs to reach a velocity of 0 first, check. Needs to have an acceleration in the same direction as its starting velocity. No. If the acceleration and starting velocity are the same, then you are in trouble. Let me reset. Well, you're not in trouble, but let me pause, clear, and let's have a starting velocity of +1 and a starting acceleration of +1. And let's show both of those vectors. If your acceleration is in the same direction as your velocity, the only thing that can happen is there is no change in direction, because the acceleration is just adding more rightness to a velocity that's already to the right. So the only thing that can happen is a change in magnitude, and it's always an increase in magnitude. Yeah, all you ever do here is speed up, and this person actually just keeps going. If you let this go, the simulation will keep graphing. I don't know if there's like some sort of built-in maximum time limit for it, but the guy can go off screen, and if you set your velocity and acceleration opposite to each other with the right ratio, you could get him to wander off screen for, I don't know, a good 20 seconds, and then see him come back later from the side of the screen. So if you want to play around with that for funsies, you can do that. So yeah, the second statement is false. And then the third statement needs to travel some distance in its starting direction first. That's true. We saw that. That was the first thing that I pointed out when we looked at it in the simulation just a few minutes ago. If an object is already moving, then to turn it around, acceleration can't just make the object turn around on a dime. By turning around, I mean like a complete 180. If you're just tilting your direction slightly at an angle, that's a different story. But if you're doing a complete 180, then Yeah, the object needs to travel some distance in its starting direction first before you can completely reverse direction. And I think that is it for that problem. Now, where do I want to go from here? Or should we call it a day? Let's see. We talked about average velocity and average speed. We talked about weighted averages. Maybe a little too much. Average velocity on a position versus time graph and the significance of slope. We talked about that. We talked about average versus instantaneous velocity. And instantaneous speed is just the magnitude of the instantaneous velocity. So if they ask you to calculate speed from a curved graph, you do the same thing. You draw a line that just barely grazes the graph at that point and estimate its slope, and then just take the absolute value. If it's a negative slope, you just take off the negative sign, and there's your instantaneous speed, in case I forgot to comment on that. The concept of acceleration and the three possible effects: change in direction, change in magnitude, or change in both. We did discuss that. We wrote down the equation for average acceleration, and we didn't do much of anything else with it. I think I want to wrap up with that, actually, so that next time we can just go directly into the equations of kinematics. Yeah, let's do that, and then we can call it a day for this week. So let me switch back to document camera. Now let's play around with this average acceleration concept. I have a book problem that will help us ease ourselves into this idea. Let's see which page it was on. Yeah, here we go. So they drew a velocity versus time graph. Do I still have the backside of this? Yes, I do. We've got the velocity versus time graph for an object moving along a straight path is shown in the figure, which I will copy. And then it says, find the average acceleration of the object during the time intervals 0 to 5, 5 to 15, and 0 to 20, and find the instantaneous acceleration at 2, 10, and 18. Okay. Not a huge leap if you understood average and instantaneous velocity from a position versus time graph. This is basically just the next tier over. Okay, probably should have drawn that a little lower, but it's fine. We have, I guess it counts by twos, down to -8 and up to 4. So 2, 4, 6, 8. Yeah, the spacing on those is not very equal. Okay, let me draw that a little lower. So that's 2, 4, draw that a little higher, so 6, and 8. There we go. Yeah, I messed that up pretty badly. There's -8, -6, -4, and -2. I need to make sure my 4s don't end up looking like 9s. And then 2, 4, a little bit lower, 6, and 8. Okay, and then we have time. They just count by fives, it looks like. So we've got a 5-second mark over here, and then a 10, a 15, and about here a 20. And they drew up until about 5, kind of straight. It just curves a little once you hit 5. Just kind of curves a little. And from 15 to 20, about the same thing, all the way up at 8. Let's see, somewhere around here. Something like that. And then, let me move this out of the way. Great. Accidentally dropped a pen. I'll pick it up later. We get something like that, and then they actually show it curving a little bit around here so that it's not exactly a sharp turn. It's more of a realistic graph that way. Let me pick up that pen I just dropped. Otherwise I might end up stepping on it later. Okay, there we go. So it said, find average acceleration for the object, and this is, by the way, for the axes. We've got velocity in meters per second and time in seconds. Velocity in the typical units of meters per second and time in the typical units of seconds. When in doubt, convert your units to meters and seconds and kilograms, and you should be good to go for most of Physics 1. Occasionally, it might be worthwhile to keep things in feet or miles, but cases where you would be better off doing that are few and far between. Find average acceleration from 0 to 5, 5 to 15, and 0 to 20. Find average acceleration. I'll rewrite the definition. Average acceleration is equal to change in velocity over change in time. It's another example of scalar multiplication, by the way. You've got a vector equals a vector times a scalar, the scalar being 1 over the time. Dividing by time is the same as multiplying by 1 over it, and 1 over a scalar is just another scalar. Just felt like pointing that out. Find from 0 to 5. So from 0 to 5, we've got velocity at 5 is -5, so A from 0 to 5. Velocity at 5 is -5, give or take, minus velocity at time 0 is also -5. Over the total time is 5 seconds minus 0 seconds, so not surprising, it's just the slope of this horizontal line, and as you should remember from algebra pre-calculus, the slope of a horizontal line is always 0. Okay, and then they said from 5 to 15 seconds, and then from 0 to 20. So from 5 to 15, average acceleration from 5 to 15 seconds is equal to velocity at 15 is approximately... Oh, wait. I just realized I copied the wrong numbers. These velocities were 8s. They were negative 8s. Glad I caught that. What was I thinking? I was looking at the wrong axes. Anyway, that little goof aside, the velocity up here is positive 8 minus the velocity over at this point is about negative 8. 8 minus negative 8 is 16, and then the time, 15 seconds minus 5 seconds. So that's 16 over 5, or no, 16 over 10 rather, which is 1.6 meters per second, or meters per second squared. Actually, let me go ahead and show that in case that's still bothering some people. If I do meters per second, which is the units of velocity divided by seconds, then I can just multiply by 1 over a second on the top and bottom. Seconds times 1 over seconds reduces and cancels to a 1, and then you get meters times 1 over seconds times seconds equals meters over seconds squared. But do remember that it's originally meters per second because that's actually the more intuitive way to think about it. How many meters per second does the velocity change each second? I feel like write it as meters per second squared, but read it in your mind as meters per second so that you remember the meaning of it, what it actually means. And finally, they asked us for average acceleration between 0 and 20. Okay, let's see. This time I'm just going to draw an actual line. So from 0 to 20, like that, if I draw a dotted line between those 2 points, I'm going to try my best without a ruler. I think I got it. Yeah, the slope of that blue dotted line, give or take, what would that be? So, final velocity is 8 minus initial velocity is negative 8 over final time is 20 minus initial time is 0. So that's going to be 16 over 20, half of 1.6, or 0.8 meters per second squared. And then part B of this question is asking us to find the instantaneous acceleration at 2 seconds, 10 seconds, and 18 seconds. Pretty easy to do. At 2 seconds, you're somewhere on this horizontal part, and we know what the acceleration is here. It's just the slope, which is 0. So we know at 2 seconds the instantaneous acceleration is 0. What about at 10 seconds? At 10 seconds, the acceleration is the slope of this line segment. At 10 seconds, you're on this upward slanted line segment, which we calculated earlier, has a slope of 1.6 meters per second squared. So that would be your instantaneous acceleration there. And then at 18 seconds, you're somewhere up here. You would have an acceleration of 0 again, same explanation as we had here, horizontal slope. Okay, that's simple enough. Now let's introduce a very, very simple one-dimensional motion problem. We have a car traveling in a straight line, and this will be what we wrap up with for today. A car traveling in a straight line, that's important, has a velocity of positive 5 meters per second at some instant. I will call this the initial velocity. Positive 5 meters per second. And of course, if you prefer to call this V1 or V0 or something like that, then feel free to do so. Use whatever notation works for you. As long as you stick with something that works and is easy enough for you and others to understand, you'll be good. I think I already gave my spiel about notation in the first stream when I talked about getting used to the notation of some of the YouTube channels recommended in my course plan. You're going to see different people having different preferences for their notation, but as long as you understand the concepts, you should be able to look at anybody's notation and be able to understand what they're trying to say, even if it differs from the way you usually write your variables. Anyway, after 4 seconds, its velocity is 8 meters per second. So the total amount of time that passed, you can call it the change in time if you will, or just time. The delta is, you don't really need to include it every single time, if you assume the starting time is 0 at least. So after 4 seconds, its velocity is 8 meters per second. So V final equals 8 meters per second. What is the car's average acceleration during the 4-second time interval? Oh, actually, wait. No, this isn't the problem that I wanted to wrap up with. Hold on. I'm thinking of a different one. Am I looking at the wrong book? I very well might be. Oh well, okay. I was expecting this to be a slightly different problem from what we just did with the graph, but okay, it's just they gave you numbers, subtract the numbers, divide by 4, and you're done. Average acceleration. I'm probably going to stop using the arrowheads on velocity and acceleration at some point starting next time, because we're going to be working with one-dimensional motion, and there are only 2 directions, which we will usually express with positive and negative. So the arrowheads are just kind of, they just kind of slow us down for no reason at that point, because we don't need to be constantly thinking about the direction when there are only 2 directions to think about. But yeah, if I end up doing that, that's why. I'll probably bring it up as I do it next time, but just in case I forget, I'm saying that now. Acceleration average is just going to be 8 minus 5 over 4, and we are good to go. 3/4 or 0.75 meters per second, meters per second squared. I thought this was going to be a problem where you're given the acceleration and you need to calculate the final velocity, but we'll be doing plenty of that next time when we go over the equations of kinematics anyway. I was just hoping for one where we could do it just with the average acceleration equation. Oh well, I guess that's where we'll have to wrap the topic up for now. Yeah. Let me read. Hold on. This might be the one. The engine of a model rocket accelerates the rocket vertically upward for 2 seconds as follows. No, that's not the one. I could have sworn there was one in here, but I'm blanking on where it was. Oh well, let me see what we can do for homework and then I will send you off. So let's switch over to that screen. And let's see what we can do. So Chapter 2, Kinematics. If we skip down to the conceptual questions, let's see. So we've covered displacement. We've talked about vectors and scalars, so those are fair game. Time, velocity, and speed we've spoken about. We've touched on acceleration. Not constant acceleration, but yeah, up to, so any of the problems listed up to and including 17. I think I listed all the conceptual questions, so everything from 1 to 17 is definitely fair game now. Next time we'll mostly focus on one-dimensional kinematics in the horizontal direction. I don't think we will do falling objects next time. If we do, maybe we'll just briefly touch on it, but chances are, the way I usually do things, we're gonna derive the equations of kinematics because I think derivations are important, even if a lot of teachers feel like they're not worth the time. I do. So we're gonna look at some graphs and derivations and all that good stuff. We're going to start off with probably velocity versus time graphs to see what we can get from them, because we just looked at one and saw how the slope of that graph can give you average acceleration, but there's also another feature of the graph that can give you something valuable, which we will dig into next time. So yeah, everything up to section 2.6 is fair game, and if you want to read ahead and at least try some stuff from section 2.6, that would not be a bad idea. If we scroll down over to the problems and exercises, same thing, anything in the list from 2.1 to just before 2.6. Wait a minute. Where is 2.6 on this? Did I misread the... Wait a minute. Oh, they skipped 2.5 here for some reason. Okay, so everything up to and including 2.4. So yeah, any problems on the recommended list up to problem and exercise 19 should be fair game now. And if you read ahead, you may find it worthwhile to at least attempt some of the problems under section 2.5. And I think that should be it. Yeah, and then where's the... Oh, wow. There are a lot of problems leading up to 2.7. So, yeah, 2.7 is probably not going to be next time. It's probably going to be the week after next when we talk about vertical motion. We'll keep it horizontal for next time for the most part. At least that's the plan, but we'll see how time goes, and we'll just go where our time allows us to go. Any other comments that I wanted to make before I end things for today? Well, I'm not actually ending things because I actually want to do some stuff after this, but It's not directly related to what we're doing. I'm going to cover some problems that I assigned to one of my students, so if you want to stick around for that, you can. But for the rest of you, this is probably where you can leave. Class dismissed. I'm going to stop this recording and start a separate recording, and I'm probably going to upload this next section as a separate video. Oh, and speaking of which, I'm probably going to have to spend the rest of the night going over and time-stamping the recordings from the past couple weeks. So if you've been waiting on that, that's coming. Anyway, class dismissed. I will see you next week.